Hi everyone, my name is Hesham and I'm a doctoral researcher at the Institute of Clinical Molecular Biology. I'm basically developing AI and machine learning based tools to better understand the immune system. Over the last 10 years or so, there has been a revolution in the field of AI and also in the biomedical field driven by deep learning. So I made this kind of small discussion today just to introduce the concept of AI, how AI is working, what are the basic principles of AI and how it's related to the biomedical field. So let's start by introducing some basics. One of the first basics we're going to introduce is the concept of a function. So what is a function? Well, basically a function is a very beautiful mathematical creature where you have an input and an output. And a function is just a relationship, it's just a map that maps from an input to an output, as shown here. This function has this kind of input and it relates them or connects them to an output. You can also see this function here, how can I say, in a live version, where in the x-axis we have set the input to the function, and the y-axis we have produced the output of the function. And what's happening here, you see this kind of blue dot that move and show us if we give the function, for example, 0, it's going to give us 0, but if we give it 1, it's going to give us 1. If we give it 2, we are going to give it 2, etc. We can also control the function of parameter more or less the same way you control the setting of your phone. So in your setting, you have the same display, but you can have higher or lower intensity of the light. And this is a parameter. You can do the same with the function. Some function has parameters, as this function here. This function is the same old guy we have, x squared, but it has one parameter called p. And based upon this parameter p, you can basically change how the function map the same input. It's going to map it to a different output. And if you look here, for example, we're going to see that as the value of the parameter starts to move from -1 to 1, the mapping of the function from the input to a different output is changing by following the curve. Of course, these are the functions that all of us are familiar with from high school. You can also have more fancy function by just combining and composing simple functions. Let's look at this one here, quite a cute one. So this is a function that basically has its input called t, and it mapped to the x and y. It's actually two functions that map to x and y. And by changing the value of the function x, we can just have this kind of parameter. We can basically have this kind of heart made by the function. So far, we have introduced the concept of a function. We have introduced that a function is just a map. We have then introduced the concept of parameter. The parameter can control the mapping of a function. We have then introduced the idea that you can compose function and you can combine function to have much more complex mapping. What this relates to artificial intelligence, or how this is related to artificial intelligence? Well, let's fire up our discussion by a small example. Let's assume that we have this task. And the task is really simple. We have a picture of a cat and a picture of a dog. And we want to ask our computer, can you classify the cat or the dog? Which is which? For us humans, it's really easy. Our brain is really, really good at detecting pictures and classifying visual input. But to do it from a computer perspective is a much more difficult task to be done. It took us a very long time until convolutional neural networks start to kick in to do that. So how would you do that? What you are going to come up with is a function. So let's assume that we have a function. What this function should do? The function should take the input, which should be the picture, and it should produce the output, which is the label, a cat or a dog. Good. Not really. How can we come up with a parameter? So that's the challenge at the moment. You already can have a function, take an input, but how can I come up with such function? How can I come up with a parameter of that function? In order to introduce this, we would have to introduce the concept of supervised machine learning, or basically how supervised machine learning work. The idea is quite simple. We have a picture and we have a label associated with this picture. This label can be, is this picture a cat or a dog? Is this picture a cat, dog, or a horse? You choose your pet. And then what we are going to do, we're going to take this picture and we give it to the machine. But now you might ask yourself, now wait a second, you already had a problem that you cannot come up with a function or a parameter. Yes, that's true. I don't know the parameter. But so what would I come up with? I would just guess some random value. So it's just parameter at the beginning are random. And what you are doing now, you are taking this function and you are going to give to this function that would just like, randomly say it a cat or dog, because it's just random parameter. What I'm going to do afterward, I'm going to take this kind of random prediction I produced and the truth, what should have been produced, and compare them. And this is a task of the loss function. So this loss function here is basically something that compare between the prediction and what is known, what is truth. And it tells you how much error you made. You predict it to be a cat and it's a dog, or the other way around. Now, you have an error. So what you do, you have something called an optimizer that would take the parameter, take the error that you made, and change the parameter so that when you have a second picture, you can basically map them more correctly, or you can minimize your error with each example you see. From a biomedical perspective, classifying cats and dogs are cute, but not that important. So we really care about people, and we care about patient and classifying disease. So one of the applications that people was really excited about was for image diagnostics. For example, through the X-ray. So this was one paper that just been published last year by this group in Stanford, where they basically used deep learning to classify the X-ray into pneumonia or not pneumonia. Thus, there is a pneumonia, and they achieve something that is really comparable to the performance of a physician. But I do want to stop here or give you the illusion that it's only used for image. Actually, the abstraction we have introduced so far is so much powerful that you can use it to anything. Let's try to summarize the abstraction we come up with. So first, we have the data. For us here, because we are using supervised machine learning, a data is just a pair of values or a tuple of values. We have an input and output. This input can be your healthcare record, your genetic data, your proteomic data, anything. And this label can be the predictions or the targets. For example, like, are you diseased or not? Do you have a cancer or not? Any measure you want to think of. And what we are going to do afterward is we are going to basically use this data and try to learn a model or a map or a function as we introduced before. We use the data to learn how we can map from this input to an output. Now you might ask yourself, okay, why this is important? Why should I care about that? Well, this is important because in many cases we don't know the label. I just want to look at the input and I want to basically look what should the output be. For example, if I'm making a prediction about your data when you are at 25 and how much disease you are going to get in the future, I can't travel in time to know that. So I'm going to use the data or try to predict something where I don't know the target from it. And this would be the phase of model deployment, where you can basically go from the new input that you don't know the label of, you give it to the model and you make prediction. So we have three key words that summarize these three phases. The first one is collect. You collect the data. Second one is you learn from the data how to map the input to an output. And at the end, you have the prediction, where you see a new input and then you try to make prediction out of it. Now, with this keyword being introduced, there is some challenges that we need to address. One of them is data privacy and ownership. These models are really database. They are really hungry for more data, and we know that their performance improves with more data. But who should own the data? How we ensure the privacy? And this is one of the things that's really crucial to consider. A second, how we address the bias in the data. We know, for example, that not even, for example, with genome sequencing or with genetic data, that usually people with European ancestry are much more studied than people from other ancestries. How can we address such a bias that we have? A third problem would be how to make an AI product when it comes to the healthcare, for example, such as drug. When we make a drug usually goes through a very, very tedious process of a lot of pre-testing, preclinical trials, phase 1 clinical trial, phase 2 and phase 3. How can we make sure that when we develop an AI, it would have the same quality and safety criteria as when we have for a drug? A third point would be the legal accountability of a drug, or the legal obligation, of an AI, not of a drug, of a tool. So when we develop a tool that works for, patient data, how we can make sure that the tools we are predicting or the stuff we are producing there have the same legal obligation and the same legal accountability. And finally, it will be robustness of the model we produce, because as we stated before, these models are trained from the data. What would happen if, for example, the machine that we use to train the model was a different machine? The data shifted slightly. The measurement we get from the machine are quite more noisy. How can we make sure that our data are robust, are stable across countries and across different machines? With that, I hope you enjoyed the talk, and thank you very much for your time.